I'm Leonardo. I'm a architecture and urbanism graduate at UFC. Currently, I'm pursuing a master's degree also at UFC.
Hi, I am Hugo Sampaio. I have a degree in design by UFC, the Federal University of Ceará. Currently, I'm studying a master's in architecture, urbanism, and design at the same university.
The other co-authors are Eugênio Moreira, Aura Cunha, Roberto Vieira, and Daniel Cardoso, who are professors at UFC, followed by Ligia Isabelli and Adrisia Marques, who are students at UFC.
Hello, I'm Dimitri Pereira, graduation student of Architecture and Urbanism at UFC, Federal University of Ceará, and this article presents the experimentations about form, data, matter, photogrammetry, and digital fabrication at the service of safeguarding the built cultural heritage. When we talk about built cultural heritage, documentation emerges as an important safeguarding strategy, as it allows the reproduction of the information contained in the form and matter of buildings at other points in time and space. However, the use of traditional techniques, based on the direct acquisition of key measurements with analog tools to produce 2D drawings, makes the documentation process time-consuming, imprecise, and often inadequate for recording complex forms. On the other hand, the growing scarcity in the availability of craftsmen specialized in interpreting and producing artifacts from these representations raises suspicions about the suitability of this type of record to allow future reconstitutions of damaged parts, an action common to restoration processes. This is a crucial point, since the goal of the restoration process is to preserve and review the aesthetic and historical value of the monument, and should be based on the original materiality and authentic documents. It must cease in the moment the conjecture begins. In this context, digital information and communication technologies, DICTs, such as photogrammetry and digital fabrication, present the possibility of improving the way the documentation of cultural heritage is carried out, allowing the creation of methodologies based on non-intrusive techniques that do not damage the object to be documented. This work focuses on the use of a digital reconstructions using dense stereo matching, DSM photogrammetry, as a capture method, selected for being the most accessible, having as a minimum requirement only the possession of a camera and a computer equipped with some softwares. The objective of this work is the development of a methodology to operationalize the documentation of elements of high geometric complexity, common to the stylistic groups of the built cultural heritage that permeate the context of Fortaleza, Ceará, Brazil. The design of such a methodology is so soft that it can be used in the restoration process. The development approach for this work was divided into two stages. The first stage of analysis and planning starts from the identification of the problem in the present paradigm of documentation of the built heritage, expressing the difficulty of transposing geometric information in the restoration processes. For this, photogrammetric capture and digital fabrication processes are incorporated to complementary fabrication processes, aiming at the reconstruction of distinct materialities. The second stage seeks to validate the workflow propositions raised in the first, observing the feasibility of the application of these models in a local context, producing a series of prototypes in different materialities to evaluate different manufacture techniques, observe the difficulties and potentialities of the processes, and record the results. Observing the particularities of the analyzed processes and the selected tooling, it was possible to outline a standard workflow for the production of physical reproductions of ornaments from digital models. Besides obtaining the digital data, the process includes the reconstruction of the ornaments via digital fabrication, seeking to choose a cycle of restoration steps for heritage assets so as to ensure a greater permanence for built cultural systems. Observing the samples documented in the field, we sought to categorize them into common criteria related to different materialities present in the ornaments of the included buildings. The categories that we were considered as the focus of the scope of this work were cast metal, wood carving, and plaster. This classification has direct correlation to the manufacturing methods employed. The techniques involved in the manufacturing processes most common to the different ornaments materialities observed are mapped in a flow chart where one can more clearly observe each step involved in referring to each materiality. To this flowchart is incorporated a device composed of a group of steps that range from the capture and digitalization of the ornament's shape using photogrammetry techniques to its rematerialization using digital fabrication techniques. Photogrammetry using DSM was the primary technique used in the process of digitally capturing and reconstructing the artifacts. It operates by taking a collection of photographs taken from various angles of the target object as input and identifying correlations between groups of homologous pixels present in the provided photographs. The photos in different perspectives of the same object allow the comparative processing algorithm to spatialize the correlated pixels as points projected into Cartesian space. This aggregate of pixels is referred to as a point cloud. According to Grodelars, the process of generating point clouds with the DSM technique can be divided into 5 main steps. The first, photo input. Second, automatic correlation of the photos. Third, reconstruction of the preliminary geometry of the object and camera. Fourth, dense association of homologous pixels. Fifth, creation of the geometric model as a point cloud and the triangulated irregular network, TIN mesh, which is a mesh of non-rectified triangles generated from the association of the vertices generated by the point cloud, which may be textured or not. Given this process, the generated geometry is often over-detailed. When that's the case, the process of remeshing comes as an optional step, enabling the creation of a simplified version of the 3D model, reducing the numbers of faces of the mesh while retaining as much detail as possible. Acquiring a 3D model of the artifact allows for its use as a digital blueprint in processes of additive and subtractive manufacturing. Computer-aided design to computer-aided manufacture software, CAD to CAM, can interpret the input geometry and output a series of machine-specific two-path commands. This process is also known as slicing. These are known as G-code. Computer numerical control (CNC) machines, such as CNC routers and 3D printers, can receive G-code as input to produce physical prototypes of the original geometry. These digital processes were grouped and considered as a minor workflow path that allows for the translation of the artifact's shape through different materialities. Having all steps laid out, the digital processes together with the physical processes to produce replicas for the three materialities considered, possible workflows were elaborated in which the end goal was taking advantage of the digital device in the process of translating the artifact's shape from its original medium to a replica of the same materiality. To validate the device elaborated by the merging of those previous workflows, a number of case studies were elaborated where a chosen sample of each kind of materiality would be subject to a series of processes mapped on by this device, wherein the goal is that the workflow meets the two conditions. First, the artifact is documented and replicated by the digital processes. Second, the final replica reaches the same category of materiality as the original one. Limitations on the methods of fabrication available restricted the digitally manufactured replicas to be made mainly of polymers, polystyrene, and wood. This means that to reach the end product, additional processes would need to be included in order to transpose the artifact shape to its proper final materiality.
Wood. The chosen ornament for this case study was carved on the main axis wood door from the Teatro José de Alencar that leads to the metallic internal structure of the theater. It is situated in Fortaleza, the capital state of Ceará, in Brazil. As the ornament which was worked on this step, the last segment of the construction was the settlement of the carpentry and frames by the end of 1909. The most of the details are still preserved as the building has gone through some restorations. The photogrammetry process sampled 45 photographs taken by a 12-megapixel cell phone camera, given the occasional absence of a professional one. The models were generated using the Epic Games Reality Capture version 1.2. The results turned out convincingly similar to other captures, with minimal artifacts, and model cleanup was done separately in Blender. A physical prototype was fabricated using 3D printing with ABS polymer at 1 to 2.5 scale. So far, the wooden prototype has not been manufactured yet. Metal. The Mercado dos Pinhões is a market building with a metal structure, registered as protected cultural heritage by the municipality of Fortaleza by Decree 12368 of March 31, 2008. The ornament chosen is on the facade of the Mercado dos Pinhões, on the top of the pillars outside the building. The photogrammetry process sampled 37 6-megapixel photographs, and models were generated using 3 different software: Agisoft Photoscan, Autodesk Recap, and Autodesk Remake. Model cleanup was done separately in Autodesk Mesh Mixer. Physical prototypes were fabricated using 3D printing with PLA polymer and CNC milling using styrofoam, wax, and MDF. The 3D printed prototype was later used to produce a silicon mold to wax copies. The final metallic piece was produced using lost wax casting using a mold in 1 to 2 scale. Plaster. The chosen ornament was the crowning of the facade, whose hard-to-reach position above the first floor presented a good testing opportunity for using drones as a photographic capture tool. The photogrammetry process sampled 2 sets of photographs, with 180 photos and 257 photos, sampled from 4K 60fps videos taken by a DJI Phantom 4 Pro drone equipped with a 20-megapixel camera. The 3D model was generated using Reality Capture version 1.2. The original model captured most of the building facade and had approximately 26.3 million triangles. This model had some surface noise and its size wasn't handy, so it was cropped, smoothed, and remeshed into 4 different versions, with 3 million triangles, 1 million triangles, 100,000 triangles, and 10,000 triangles each. The 1 million triangles model was chosen for prototyping since it was the one with less geometry that still maintained most detail. The ornament was isolated from the model using Boolean operations in Blender and exported for slicing. Physical prototypes were fabricated using 3D printing with PLA and ABS polymers, and CNC milling using Styrofoam and XPS. The 3D printed ABS copy was later used to produce a silicon mold to make plastic copies. The main issues found through this case study were: the photogrammetric reconstruction generated surface noises that affected the physical accuracy of the model. It's unclear if the photo sampling hasn't covered enough angles, or if the photos taken by the drone while moving had motion artifacts. FDM printing generated stringing on the printed piece. This can happen especially when printing ABS and PETG. This can negatively affect molding processes and make cleanup time-consuming. The silicon molding was inconsistent, which made artifacts that could affect the final piece.
This study has allowed an exploration of the possibilities presented by the development of a methodology for documenting elements of high geometric complexity. Techniques such as photogrammetry and 3D scanning reveal complementary possibilities to this process of documentation and registration, as the form of the registered object is transposed to digital media. The main possibility explored with the incorporation of the process in this research was the manipulation of obtained 3D models as visual aids, or on the process of fabricating physical prostheses to be used in restoration projects. Experiments in producing these prostheses often rely on the presence of symmetry and repetition in the documented artifact. This way, speculation on the original shape of the ornament is more easily avoided, and a 3D model can be produced using a model of undamaged area and an undamaged one. A Boolean difference operation could be performed, where a digital model acts as a geometric operator, detecting another model that intersects with its geometry. This process generates a fragment based on the reference model, which fills the negative space of the model. A workflow such as the one described in this work, encompassing many different processes and tools, is bound to have results of varying qualities and serves mostly as a general guideline through the steps available. Its exploration, however, opens a path to the qualitative evaluation of the techniques and tools available, as well as different work paths pertaining to the recording and replicating of built cultural heritage.